to show the ropes and how to interrupt. We're going to start as well with István, who's going to talk about kind of the work that we are inspired us to put this entire thing here together. Right, István.
Yes, it's a bit maybe unusual to have the organizers give a talk, especially the first one, but
we'll get the arguments out of the way, don't you?
So I think if we're going to be talking about the dimension of conjecture, then maybe it's appropriate to start the first slide with that. So, okay, so some of you have heard part of this talk because on Porkroll I basically gave the same. So, maybe you were out on the beach instead, so it's a perfectly reasonable choice. But anyway, but of course there's going to be much more new stuff as well because it's not 20 minutes, but 16 minutes long. So anyway, there will be some repetition, probably not too bad. Okay, so I think the dimension of conjecture we are more or less familiar with, at least in the self-similar setting. So we start off with a self-similar IFS. We know that it has an attractor, so we assume everything is uniformly contracting. And given a probability vector, we also have a self-similar measure associated to the system. And we know that there's a natural symbolic covering both of our set and also an upper bound for our dimension, simply given by, for the set itself, it's a minimum of, okay, so we're working on R the whole time today. So that's why 1 appears here, and the simulation dimension has the upper bound. And for the measure, you have 1 and the ratio entropy over the upper exponent, which all of these quantities depends strictly just on the contraction ratios and the probability vectors. Okay, so we have this natural upper bound. I don't know why it's flickering like this. Everything is flirting nicely. Anyway, so right, these are always an upper bound. So the question is, when is there equality here in these situations? And so this depends on basically the amount of separation in our system, right? So there are 2 fairly trivial cases. One case is a strong separation condition when the natural projection from the symbolic space to the attractor itself is a bijection. In other words, the images of the attractor of the map by the maps are disjoint. Then we have equality. But if we have things that overlap, then there's a strict inequality. So, and basically the question was whether there's anything else that can cause this kind of dimension drop. And I don't know whether this is like really widely believed or whatever, but generally speaking, I think we think that this is probably true that there's no other mechanism.
I don't think exactly can immediately imply this.
It does immediately imply.
Oh.
If the similarity dimension is smaller than 1.
Yeah, then it's okay. That's very important. Yeah.
So yes. Right. So of course there's been lots of work on this, and probably we're not going to go through the whole history here, but jump straight to the exponential separation condition, which was the breakthrough about 10 years ago. So just to recall the exponential separation condition, we have a constant and we have infinitely many n, such that the difference of the functions has to be bounded from below by this constant to the n. So this is why the exponential separation name, and this is true for all words of the same length. This is really annoying. All right. So strong exponential separation condition, we call it when this is true for all n. And when we negate this, then we say that it has super exponential condensation or weak super exponential condensation. So the big breakthrough result of Mike was that if you assume this exponential separation condition, then there is no dimension drop in those previous 2 cases that we looked for the self-similar sets and for the self-similar measures. And what was also very nice about this result was that explicit examples could be given where this condition can be checked. Namely, if the parameters are algebraic and there are no exact overlaps, then we know that the exponential separation
That
holds.
is strong.
Quite possibly, yes. So there have been works since on relaxing the algebraic condition. In a few works, this has been either on homogeneous systems or for the Bernoulli convolution, or Ariel's result is when, the translations can be arbitrary, but the contraction ratios still have to be algebraic. So in these situations, the exponential separation condition has also been verified. And then for a few years, there was an open problem whether it's possible to have an IFS which has super exponential condensation, but no exact overlaps. And it turned out that the answer is yes, and there's basically two different kinds of examples out. One of them is due to started with Simon, and there's also been some other works on that. And another type of example was given by Balázs and Antti. And I believe that for Simon's examples, the exponential separation can be verified due to these situations.
No, the dimension, or the no dimension.
Yeah,
The conjecture can be verified, so you can have super exponential close and have the expected formula.
yes.
Yeah, that's
What I think I want to say.
yeah.
So yeah, but in general, we still don't know the full picture. So there's this strand of research, and there also has been, of course, many different generalizations of the results. So one instance is to look at the IQ spectrum of the self-similar measure, and there as well, there's a natural upper bound for this, so similarly, Pablo was able to show that the exponential separation condition in this case as well implies that this inequality is actually an equality here. There has been work since on higher dimensions as well. This is still self-similar. And then there's been a start in doing stuff which is nonlinear. Okay, so we have results about Möbius transformations for the set, the measure, and the IQ spectrum as well. And we are going to be hearing from Haoji, I believe, about generalization of Usuki's result from Möbius to general analytic functions. So that's going to be very interesting. And then there's also, which was our main motivation, was Ariel's generalization to real analytic conformal IFSs on R. And very recently, Zhao with Ariel has generalized it to the planar case for holomorphic maps, and he's going to be talking about that here. And then, what's something which we are not going to be talking about at all, but just good to know that if you go outside of the self-similar or conformal world into the sub-fine stuff, then everything is much more complicated, but that's not going to be our topic for this week. So Ariel's results slightly a bit more concrete and formal. So for conformal IFSs, we just have to generalize the notion of similarity dimension, the Lyapunov exponent as well. In the following way, we have the definition of the pressure function, which I'm pretty sure we're familiar with. And then the conformality dimension generalizes the similarity dimension by being the root of this pressure function. All right. The entropies of the probability vector is just the usual, what we always have, and then the Lyapunov exponent is the average exponential contraction rate of the system. Okay, and then the result of Ariel was that if you have a self-conformal IFS on R, which whose attractor is not a singleton, so all the fixed points are not the same of all the maps. If the exponential separation is satisfied, then there's no dimension drop. Okay, and in this paper, there's also an example of a one parameter family of analytic IFSs, which under a mild non-degeneracy condition, you can show that there's no dimension drop outside a set of parameters of zero Hausdorff dimension. So this was basically the starting point for us, where we started, and the motivation for our work was, okay, so knowing this, let's understand this exponential separation condition more in the setting. So what we were asking whether, in some sense, this exponential separation condition is a typical condition, and as in the example of Mike of algebraic parameters, can we give concrete examples of nonlinear IFSs which satisfy the exponential separation? So this was our motivation. And so these are the main results that we got. So the first one is about the typicality. So in the beginning here, the slide is just like the formal setup that we are using. So just stating that we are having analytic functions on the bar, which map the unit interval to itself, and we are uniformly contracting. So all contraction ratios are separated away from 0 and 1.
So you really mean that there's F is complex and analytic and it's a proprietary R?
Well, you're just thinking about it that it's defined on a small neighborhood of the unit interval. But if you only look at it as acting on the unit interval itself, then there it's a real complex, so it's mapping that into itself. Outside of it, we don't really care.
Yeah, so it fixes the interval. So the interval is reacting to itself, otherwise it's real analytic in its tiny neighborhood.
But it's even complex and
But on the tiny neighborhood, it's also complex.
Then retreat to
oh,
So it's a somewhat more stronger condition.
so there's a complex in this.
Yes,
It's not.
yeah, that's what.
Because of the radii of convergence and stuff. Yes.
Oh, yeah, that's what this is. They're the smaller of a complex.
Yeah, and it's strange that F is defined only on the real line, but
So
you can
but you can extend it.
yeah, so extension of this. Okay.
Yes. And then on this space, because we're going to be working, so the topology that we're going to be looking at is a C2 topology. So the distance between two maps is given by the supremum of the difference plus the supremum of the difference of the derivatives and also the second derivatives.
And we have learned why you go exactly until the second derivative.
It will become, I think, it will become apparent, yes. So you have to go this far, but this far is enough. Yes. So this is where things start to look different. Okay, and then this is simply this space. This is just those IFSs where the cardinality is just how many maps you have, and each of them are these nice functions. So the typical result, which sort of answers your question to some extent, is that in this topology, the set of IFSs will satisfy the strong exponential separation condition contains an open-ended subset. Okay, so in particular, there is a big set where we have no dimension drop in topological sense. So this is the typicality. I will say a few words about the proof of this, but this is not.
Yeah, sure. I'm just asking whether C1 is not enough. Question mark.
Right. We haven't thought about that, I think.
Oh, you mean for the topology?
Yes.
Yeah, the one IFS requires.
Yes. Yeah, because so you will see that in the definition, yes, the dual phase, the second derivative of the function does appear. So I don't think we can go below.
Although there are these generalized derivative like things which might occur, but I have no idea how it would be. So yeah, just in case the second derivative makes life easy.
Yeah, so there will be a few words on the proof of this. But I will be concentrating a bit more on the result, which gives us a sufficient condition, which we can actually check. Yeah.
we could imagine replacing the second derivative by just difference, taking difference and dividing by the, not taking the limit. Then you would get a sort of IFS with two variables, in X and Y.
You mean not generalize the two IFS?
Yes.
Cool.
It's used in our paper with Thomas and Sample.
Okay. So guess maybe we'll hear about those.
Yeah.
Now we
Now you regret.
Yes. So the submission condition, so just a bit of notation. So we will be writing words forward and backward directions as well. That's why we need to make a distinction. Okay, so when I write something like this, I from M to N, depending on whether it's an increasing sequence or decreasing sequence, I'm writing it forwards or backwards. Okay, so if M is smaller than N, then it's increasing. If M is bigger than N, then it's decreasing, so it's written backwards. Okay. So in particular, if you see something like this, then this is just writing the word backwards like this. Right? Okay, and now we are going to introduce a function, this hi, which looks like this ugly sum like this, where again, just be aware of the order in which the indices are appearing over here. And this is where the second derivative appears. And if this, you don't really see what this is, then if you think about a finite length word, then this is actually just the second derivative divided by the first derivative. In other words, you're just taking the log of the derivative and you're seeing how that changes. Okay. And in particular, this function does not see a difference between two functions if they are just a constant multiple and translate of each other. Okay. But in any case, this is the function that we use to be able to show that a analytic IFS satisfies a Strong's exponential condition if for any two words of the same length, finite or infinite, if you take the difference of these h functions, you only need that the supremum of it is bigger than 0, then that already is going to imply this strong exponential separation condition. So this is one formulation of it, and as we will see once the dual IFS is introduced, that you can do this in different ways as well. Okay, but for now,
so isn't the the negation of that would mean that HIFS and HJFS is the same, right?
yes.
And doesn't that imply something very strong? I mean,
We will see that.
so it's not exact overlap.
No, it forgets about a lot of things which take the second derivative first.
Yes.
Yeah, but I mean, so doesn't it mean that it's essentially there is an overlap in some sense?
Not necessarily in the original, but in terms of the distortion that you see from these maps. But the original map does not have to have the same thing.
Yeah, okay.
Yes. Yes, like in particular, this theorem doesn't say anything about self-similar IFSs. Right? Because if you have two similarities in your IFS, then both of the h functions are just 0. Okay.
Oh, I see.
So it doesn't say anything about self-similarness.
So if you favor the strong exponential separation condition, so somehow retrofit reason means somehow one of the ways I interpret this result is if you fail this, then somehow being super exponential close means that your first and your second derivatives are also very close in some suitable sense. So, and somehow you focus on the second derivative and you say, and this is somehow saying the second derivatives are well separated, so you can't, your level 1 maps can't be close to 1. So what's stopping you from saying taking the kth derivative? Right, somehow, what if I, instead of the second derivative here, I took the kth derivative, it feels like a similar statement with Hulk, as somehow being super exponentially close with your 2 level n words, you could take this a few levels lower and say the derivatives have to be very, very close as well. And then that could be reinterpreted in terms of some HIs, but I don't know, HIK, where you have maybe something similar.
This is exactly what happens. Yeah, this is how the proof goes, that you go with the higher derivatives, because basically what you are describing, there are also for the third, fourth, and so on, these kind of weird operators also, but all those informations for them are already coded in these HIs. So basically the proof for that goes like that there should be, if the original system has the strong exponential separation, then there is an extremely high derivative somewhere for HIs and AJs, which corresponds to an extremely high derivative for the functions, which are also close. For all the high derivatives are very close. And then these HIs are analytic maps. So they are also maps.
So you were saying if you have this strong exponential separation condition, then you see this.
Yeah, no. So we got exactly what István is. That for the linear systems, because of the existence of linear systems, this other direction of implication doesn't work. But if you know that there is some high derivatives there who are different, right? So if you would like that instead of the second derivative, you use the k derivative, and that system would be strongly separated, then it still would imply strong exponential separation, exactly by the same phenomenon. Yes. But already that information is somehow encoded into these HIs, because the higher derivative IFS, so the IFS, dual IFS corresponding to higher derivatives are basically somehow derivatives of HI. So there are these connections.
Why is it the case that, so you're saying that if your k is greater than 2, and some kind of analog of the dual IFS wouldn't tell you anything new from the dual IFS when k was equal to 2.
This is what from the proof seems, yes.
So then what's special about 2? Could you not define a dual
The 2 measures the curviness. The 2 measures how nonlinear you. So
excuse me, strange, we go from something special about 2, which says you can go from 2 to everything higher than 2.
Yes.
But this isn't true for 1, because this is you say for 1. So what's special? Why is 1?
So heuristically, at least, so this is so with these ages, you can forget that we cannot say anything about similar systems anymore. But we now have a condition that is easier to check and satisfy for those systems. You can also do something with higher derivatives there as well. I might say something in a few days about this, where you ignore even more systems, but then you get an even easier condition to check that tells you the strong special solution condition for these systems, but not for these other ones that you cannot check. You're forgetting some information. Like here, you're forgetting all the linearities, they are out, you cannot say anything about them. But you've just gotten a little bit further, and you now have a condition that says, at least for those which aren't substantive IFS, when they satisfy the strong special. There's a bit of a game of, hey, you can do the higher derivatives, but you will lose some information about systems where you can no longer say anything about. Okay. So what we're here for getting is just substantive systems. The least thing we could forget, apart from today's system.
And I will have a few slides about the proof of this. Maybe that will also shed some light on things. Okay, so this is the main result, and so let's see. So on one hand, this result is a key step in proving the typicality results. So that's one application of it, and the other one is actually showing systems which satisfy this condition that we give here. So let me give you a few concrete examples. So by taking the most naive kind of balance everywhere, we can state a proposition which says that if something is satisfied where you just see concrete numbers everywhere based on the system, then you can say that IFS satisfies a strong exponential separation condition. And you can actually generate examples which is going to satisfy this. So for example, you can take polynomials. So, and there's a bit of overlapping here, right? Because F1 and F2 actually have the same fixed point 0. So there's definitely overlapping. So, these three functions are going to satisfy the conditions of this proposition. Hence, we know that the strong exponential separation holds. Hence, there's no dimension. So you can generate examples like this. You can go even much wilder. So do general analytic functions. So here are three functions. And overlapping is like extremely heavy in some sense here. It's not only that the fixed points are equal, the derivatives of the fixed points are equal, and even the second derivative divided by the first derivative at that point is equal. So extremely, extremely strong. But still, it's going to satisfy the conditions of the proposition, and hence everything as follows. And something that we're actually working on right now and work in progress is what if you restrict yourself only to Möbius transformations? It turns out that in that case, this h function has a peculiar, very simple form. So it's just 2 divided by this pi, this is the pole of the function. So that's just, in this case, that would be minus 10 over 5, so minus 2. Pole minus x. So it's a very simple form. So in particular, so these three functions here again, they have very heavy overlaps in the, as in the fixed points are the same for the first two functions and the derivative is the same there as well. But you cannot have in this case that even the second derivative divided by the first derivative are equal, because in that case, the h function of the two would be identical. And then our result doesn't say anything.
I have another question. It's on the exponential separation condition, is it invariant under change of coordinates? I mean, taking a conjugacy. Thank you.
Could you
Yes.
Yes.
So if you conjugate the system with an analytic function, does the strong exponential separation hold for the new one as well? Yeah. I believe so, yes.
Yeah, if it's analytic, yes. The exponential separation condition over closed cylinders will just transfer to the same discrete.
Yes. Just say
That's what I meant.
Yes.
Yeah, I have another question to make sure I understand what's going on. So do I understand correctly that for any Möbius transformation, hi is always t2 over pi minus x?
Yes.
But does it mean that if the poles are different, then always you can apply the previous result and yeah. So that's it.
It's not that simple because you also need that the poles are different for the higher returns as well.
Yes.
What do you mean higher return?
So in the theorem, you have to have
h
for yes. And it's for all finite and even infinite words.
Oh, I see.
So in fact, we do have a condition for these Möbius transformations as well, but it's a bit more, it's very nice, but it's also a bit more complicated. I can say a few words about this at another time, but technically, so the way the poles are given, they are given of the iterates, they are given by iterations of the inverses of the original IFS. So you take the inverse functions, and that's how you're going to get the poles. And the inverse functions then, they can define you a new IFS. And if that IFS satisfies the strong separation condition, then all of the poles of all of the iterates, even though infinite words, are going to be different, and then you can actually apply results, yes.
This separation of the poles, this feels like something that will be implied by some algebraic assumption on your function sets, and how if we think about the Hoffman results, that you have exponential separation, you can apply it when everything is parameterized by algebraic numbers. But I would expect in this context, if you parameterize your Möbius functions by algebraic numbers, then the pole would also be parameterized by an algebraic number, in which case you could say these are distinct, they have separation. And would this give you some kind of algebraic Mobius transformation satisfies the dimension drop conjecture? I mean, this feels very.
It's
Good.
It's possible, yes. It might also, yes, it might also come from this inverse function thing.
Also, your condition very sensitive to the algebraic city, right?
Yeah, so it's not at all. So here, I could have given you transcendental numbers, it wouldn't matter.
Within an open set of all the parameters, there's an open set around all the parameters where this was done.
Yes, but crucially, some point in this, when you're verifying the separation for higher iterates, like the example we had before, you somehow verify the first iterate, right, and it filters down. Whereas here, you need to verify it for all iterates, which is very difficult, but somehow you're able to say, well, these are just algebraic numbers and they're distinct, then you get the separation.
Yeah, I think what you're saying is right. Then when you say that these are algebraic in the high open, those will also still get algebraic.
Yeah, but there is one obstruction maybe that we also require that for infinite. So for all the limit points, they also must be distinct. And that one, although so you have two different algebraic sequences, right? You know that they are different, but their limit might be the same. And then you cannot say anything.
It might still hold.
It might still hold, but you cannot apply that proposition.
Yeah, that can be made
Stuff later.
Yes, because it might happen that you don't need actually the strong separation. It's enough to have some controlled difference for finite words, and you are done. That I agree.
Yes, we also had an attempt of looking at polynomials in general, but that seems even more complicated to do. But there are some interesting stuff there as well. Okay, so these are some concrete examples.
How about like the graphics?
Not necessarily, because even there, the iterates, right? They're growing very fast. The exponent 2 to the something, right? So the degree of the polynomial is growing very fast, even if you just have 2 products. So there's not necessarily a big difference whether it's second degree or 100th degree polynomial that you take. Okay, one more strand of implications that our results have, which is going to be more, I think, connected to the Fourier kind of stuff that will be heard here, is about conjugation to self-similar systems. So this is just a definition of an IFS being conjugated to a self-similar one. Okay, so our conjugation function is an analytic function, and this is the self-similar system that we're conjugating to. And we say that the system is self-conjugated if you can find just 2 finite length words of the same length who are conjugated to a self-similar system. Okay, so there's like some self-similarity deep inside of it. That's what self-conjugation is saying. And then the result is that, so you are conjugated to a self-similar system if and only if all of your H functions are the same. Okay, so that's a kind of way of looking at it. And you see a self-conjugated subsystem if you can find 2 distinct level n words such that these 2 H functions are the same.
Sorry, in your previous result, I and J, which have different lengths?
No, so even here, we were always assuming, here, that they have to be the same length. Yes. Yeah, so this has sort of led to us initially to have a conjecture, like, okay, right, remember the self-similar system is a question whether you can have super exponential condensation but no exact overlaps. So the question was whether something like that can happen in the nonlinear world in the sense that you have super exponential condensation but no exact overlaps. Can that have something which is strictly non-self-similar in it? And for a while we thought perhaps a bit naively that something like that is possible actually. But this is just like a few days old, basically. So the answer to this general conjecture is no. So within the Möbius maps, we can do something very interesting, and Sascha will say a few words about that at some points. So there's some other obstruction can also happen, some kind of an irreducibility thing, but we will say a bit more about that later. So now let me finally say a few words about the actual this dual IFS. Okay, so given an analytic IFS, we are going to define its dual, which acts on the space of complex analytic functions by this point over here. Okay, so the little f's are your original IFS, the little f's are in your dual, and the little h are just analytic functions on 0, 1. And this is what it does. So it takes h at a certain point, it scales it by the derivative of the little f, and translates it by the second derivative of the first derivative. Okay? If you start to compose this with different indices, then this is the formula that's going to appear. So you are still scaling your function h at a new point with the derivative of the composition, and exactly what you are translating it by is precisely that h function that we introduced.
Is this one of your motivations to define like this?
Yes, 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 and this was like the first part where we're starting to really call this kind of like the dual IFS and this h function the dual natural projection. Because if you think about it, if you plug in the constant function 0 here, then this is just h. So this is really like as if you were, as if in the usual IFS world, taking your natural projection. But this is taking it in this more complicated space.
Is this the reason why you had to choose these kind of backwards words?
Yes, so maybe I did not say a word about that word, right? So if you write your words forward, then you're always going to converge to a single point. But if you write them backwards, then you're jumping all around your attractor, like the chaos game, if you know what that is. And this is exactly what this is doing. So it's jumping all around. And you need that, so you wouldn't be able to do it the other direction. It wouldn't give information.
Makes sense also because this is a as a fractal, like you are reversing composition.
Basically, the function is false stuff.
Which pattern?
I mean, I don't know. I just say that. I mean, if you compose two functions and then you get the associated dual IFS, it will reverse the composition.
Or
Basically, the chain rule, once you expand the chain rule, you get the last factor and you just bring that by out.
Yes. Yeah. Right. And so the reason why it's also justified to start calling this also an IFS is because you actually do have contraction. Okay, so if you take, so you see here, because our original IFS is strictly contracting, these guys are also actually contracting on this larger space. So in particular, it is true that you are going to have an attractor of this in the sense that we are used to, that this attractor is the union of the images of itself with respect to these capital S. Moreover, this natural projection, this is actually in the space, so this is an analytic function. Okay, what you have here, this is analytic. It also has some nice further properties, which I will detail a bit. In particular, it is fully continuous. So it is true that if you take the image of the symbolic space with respect to all of these H functions, then you actually do get the attractor. So it is mapping onto the attractor, just as it does in usual IFS words. So So this is why the terminology we think is justified here, and there are really animals with the setting that we are more used to, I guess. And in this,
but the dual is not the original.
that's true. That's true. I don't know. Yes. But in some sense, somehow the dual, okay, it does, okay. So in this world, we can now restate our theorems in the following way. So in this world, you can also define a strong separation condition. It's just the same that you would think what it is. So you take your attractor, you map it with the maps in the dual, and if they are disjoint, then you say that you have a strong separation condition. And so just by this definition, it's not totally obvious how we actually get this theorem here, but I will show you what are equivalent formulations of the strong separation in a moment, where it's going to be obvious that actually our sufficient condition can be restated the following way, that if upstairs in the dual you have the strong separation condition, then downstairs on your original IFS you get the strong exponential separation condition. Moreover, the conjugation stuff, remember that you are conjugating to a cell similar if all of the H functions are the same. That means simply that your attractor is just a singleton dual. Okay? You are self-conjugated if and only if you have two finite words of the same length, such that the two corresponding compositions have the same fixed points. Okay, so that's how you formalize things in the language of the dual IFS.
Just to say, so, and also just having the same fixed point does not mean that the H's are the same.
Yes.
Take the periodic words, then it will converge to the same function. But it might not, it might be possible, I mean, there are examples where you have the fixed point, all of them, well, they can be the same, but H functions are all distinct, but once you transition to the limit, then the periodic words can easily some contact. But yeah, the fixed point is the bottom, not the H, but it's the fixed point.
Yes.
And if you like fail the strong separation condition for the dual IFS, assume some overlap with the dual IFS, that's how we're talking about the IFS.
I have a strong suspicion the exponential separation condition of the dual also implies, so it can weaken the condition somewhat. I think we worked some calculations. This actually is still the case, but the strong separation condition I want to check rather exponential on that dual system as well. But the same argument should hold there as well, during separations and
These phenomena are all ongoing in progress work on the modules case.
that is a very good question.
Now, I think that what Simon said, that in this algebraic case, if the poles are exponentially separated, in that case, this should suggest that the dual IFS is exponentially separated. And if everything goes well, this should also have some implication on the original IFS using these things, but it's not done. So yeah, this is a strong suspect that exponential separation of the dual system should imply exponential separation for the original origin.
I actually meant like more the recursive. Okay, so if you assume some separation of the original, does that imply some kind of separation of the?
No, exactly the similar system is the counterexample for that.
Oh, yeah, okay. Yeah.
Anything else? So the next, okay, so now what I will go into a little bit is about equivalent formulations of the strong separation and the dual. So even in upstairs in the dual world, for the analytic functions, we can define cylinders. That's just the way that you would think you would do. So this little k and big K, they are just the constant functions. And so we say that an image of this cylinder are disjoint by two different maps Fi and Fj. Well, if you take a look at these two different pictures, right? If they are disjoint, then that means that you can take a slice, a vertical slice, where they are different. So where they do not overlap. Okay, because here I would not be able to draw any kind of analytic function which goes through both of them at the same time. Whereas in the right-hand side, it is possible to draw an analytic function which goes through both of them. Okay, so this one is not disjoint, but this one is disjoint, even though it seems like there are some overlaps in it. Those are not really overlaps. Okay, so this is what disjointness of cylinder sets means. And then the equivalent formulations of the strong separation condition, one of them is the one that we use in the proof, is precisely using these disjoint cylinders. So you can find two constant functions such that if you take a high enough iterate, they're going to map. Okay, so they are far enough away that already on the first level they map strictly into themselves. Moreover, you can find high enough iterates at level n such that they're all cylinders are already disjoint. It's okay. And this is the same as this formulation with the H functions, and this is precisely what we saw in the original statement of the theorem. Okay, that these H functions, either for finite words or for infinite words, they are not identically the same.
But then it's enough to check for finite loads. Do I misunderstand something?
So could you repeat?
That because 3 and 4, they are, I mean, any of them are equivalent to 1. It seems to me that we don't have to check. I mean, if I forget the 4 and I want to check for the 3, then it's enough to take 45 times. This is what your lemma seems to state, right? Or I misunderstand. Or it's a typo.
No, because of the strong separation, it's an open conditional. Yeah, this is why it's enough to check some finite. Yes.
It might be sufficient to check the first level, just because
Yeah.
we're still in a weird space, in an infinite dimensional space that you have to check some levels that from some level onwards you have the separation.
Yes.
It's not quite the same as in RV.
No, it's quite the same in the sense that in RD your open set might be extremely weird, right? So we like the open set condition for Sierpinski, Gaskip, and whatsoever, where our open set is nice and tidy. But it can be very, very disgusting. So basically, if you have nothing in your hand, just tiny little balls, and you have to go to a very, very deep iterate, but finite many steps to check the strong separation. So you are right, it's enough to check the strong separation for finitely many steps, but actually we need to show the strong exponential separation for also the limits. But of course, yeah, so actually the infinite sets then are there because later on the parts we also use them, but yeah, there is this implication.
One can, for example, like we have in this other, the sufficient condition, you can increase the condition to also then ensure that on the first iteration, the strong separation condition will be satisfied just by forcing even more separation.
Basically, this is what the proposition is about.
Yes.
You have immediately.
Yeah, I remember I mentioned that HI is fully continuous. So is it necessary to prove this?
Actually, HI is analytic. For general C1 plus alpha, it's further continuous.
With respect to the coding.
Yes. Oh, with respect to yes. Sorry, thank you. Yes, indeed.
So can you define cylinders instead of with the constants K and K, could you define them in terms of functions and get the same state? So your function being bounded above and below by two other functions, the same.
I guess so, yeah.
Yeah.
Yeah, the only thing what you need is that this, let's say that it's dry, generalized dry, is invariant, that all the maps are maps it into itself. But I would guess that the boundary is a constant or not doesn't really matter, because if you go to the high iterate, you will only see the HIs, and the effect of these boundaries is quite negligible.
Mapping this, as long as you're mapping the strips within the strips, or any analytic functions in there, as long as that is satisfied, they can be whatever shape.
I could take something more generally like
It might be useful to show that you have some separation at the very first step, but not for really going to very high. Because the,
so if you consider the fixed points or the different FIs, you think of those as functions, and it's a small neighborhood of each one of these.
yeah, but the fixed points can cross each other. So if the lower and upper fixed points are just one single function, then yeah, this is naturally what happens, like an interval on the real line with analytic maps. But here, these maps can cross each other, so they can intersect each other, these maps, as many times as you wish. And as soon as your wish is finite.
Fixed points are functions.
Yes.
But they're just
Yes, I guess I'm thinking that somehow. Is there a would there be like a fifth version of the statement which you could formulate in terms of the fixed points of the FIs? So which somehow I don't know would be.
I would guess so. Yes, it's possible.
I guess my next question would this be particularly illuminating, because somehow you have your fixed points and you would have some strange behavior of the fixed points, and maybe this is a verifiable condition.
Yes. So this is what I would believe, that you can really verify it via looking at the fixed points, but
you also need to know that it's strongly contracting enough around that fixed point so that you get some of these tubes, these windows not overlapping, or some other
or some other uniformity of that or something like that. Yeah, but maybe it's not really easy to use that for later purposes.
Would this be particularly explicit in the Mobius context, do you expect, or would it be just as difficult to?
It's a very, very good question. Yes, next one. Yeah.
For Mobius transformations, is there some condition on like the poles of all of the iterates of the maps that implies conditions 3 or 4 here, but then implies a bit
But for Mobius maps, yes, so I think that's so if you take the inverses of these functions, and you look at that as an IFS itself, let's assume that, let's take a look at that. What is true is that the poles of the compositions, you can obtain them as images of the poles of the original IFS with respect to the functions in this inverse IFS. Okay. So, in other words, you have this pole Pi. What that's going to be equal to is you take a composition of the inverse functions. I'm not exactly sure in what order. I think it's in forward order like this. So this is the pole in the original IFS of the function corresponding to index IN. These are the inverse functions. And this composition here, this tells you the pole. So this is the pole of the original one. Okay? And you want that all of these guys are distinct. So in particular, if this IFS here, of the inverses, this one here, it satisfies the strong separation property. Then you know that all of the poles and all of the limits of them as well, they are distinct. Hence, all of the h functions have to be different, so our so that precisely shows that this condition 3 and 4 that they are satisfied. So that's the condition for the Radius transformations. So I have not gotten even as far as I did on Portugal.
I know that you ask a lot, you know a lot than me.
As the accidental chair. According to the schedule, this is the time.
Yes.
I guess we can still have a little bit of something to flexible now, but we shouldn't go around in the afternoon when we.
Yeah, we probably wouldn't be able to go to lunch. Like much before 12 anyway.
Okay, so
Because that place is not open, I think. So for like 10 minutes, I think I can still.
So maybe we can negotiate another 15 minutes of this, and then go to lunch.
The chance of color.
Yeah. That's why you should. So maybe let's say 15 minutes. But if we still have a question about proof, yeah, instead of all the other days,
It won't get to the end. I just think two slides. So right, what I'm going to say just a few words about now is the rough sketch for the typicality. So that was just this theorem. This one. They didn't see to the project evidence. So right, we have to show openness and denseness, two things.
Yeah, but actually you show the openness and denseness of the strong separation of the dual IFS.
Yes, so
Sorry, but when that result has shown that they haven't already heard about a dual, so that statement is about the dual, in fact.
no.
No, because you prove that via the dual. So showing
Yes.
that the dual IFS having strong separation is an open and dense set, you know that there is no dimension, very strong exponential separation contains that.
Yeah, so what you do. Very roughly, this is what you do. So you are given an arbitrary analytic IFS. I'm going to show you in the previous slide how you kind of bump this function out of this, you change it a little bit to get another function, which are going to be the GIs. And you lift, this is the function GI, this is the IFS which you lift up to its dual. And for this dual, you show that the strong separation condition holds. And this is how you get denseness for the Hausdorff. Okay. The openness is more straightforward. Okay, so you can just do that. But this is the strategy for the denseness. And this is the key point, the second point. So how do you change your function slightly so that you get a function, an IFS for which you can show the strong separation of the dual? And so this is just a statement of that proposition. So what it says is that you give me any analytic IFS, we're just talking about a single function right now. You give me any analytic function. You give me any 2 points, sequence of points on the unit interval of different cardinalities or whatever, this y and the z, which are disjoint. You give me any epsilon and any delta. What I can do then is I can give you another analytic function, this g, which satisfies these things. So on these special points, the 2 functions are equal. And in general, the functions differ by most epsilon, so they are close. A similar thing is also true for the derivatives. So that's what's true. And the second derivative, so this is why we have these 2 different sets of points. So on one set of the points, so on the z, we have that even the second derivatives are equal. But on the y's, we are bumping the second derivative over the first derivative by a tiny bit. Okay, so here we have this separation happening, which is going to help us separate the h functions. But nevertheless, even the second derivatives are still close. Okay, so this is how we get different analytic function, which has very nice properties, but is still very close to the original one. And this is the one that we can then lift and then show that strong separation works for it. But actually, the proof of this I'm not going to show. It's analysis, really, so there's nothing too special about it. You sit down and you sort of do it. What's non-trivial is to guess, I guess, what should the form of the function g be that you are searching for? Well, what should it look like? But after that, once you have that, then it's actually, you calculate derivatives and you do the stuff. Okay, so that's the sketch for the typicality very briefly. And then now let me say a few words about the sufficient condition. So I'm not going to say everything here as well. But okay, maybe what I will do is I will sort of go. I maybe I will go through it quickly, and then maybe if we want, we can discuss it in more detail later. So one important thing is that you can prove that these h functions, they have bounded derivatives. Okay, where the bound, of course, depends on the derivatives that you take, but still these are constants. How you prove this is by the fact that you can write the h functions up as a composition, and there's an ugly formula for the derivative of compositions. Okay, in particular, if you apply this Fadi-Bruno's formula for our situation, then you get a horrible looking thing. But you can bound everything in there and you get uniform bounds. So that's the nice thing still. Okay. And in particular, what a corollary of this boundedness is that if you take the derivative of the same word, but at different points, then you have this kind of Lipschitz kind of bounds. Or if you take the kth derivative, but you change the words themselves, so the I and the J, at the same point, then you also have a upper bound like this, where the common length of the word appears. Okay, and these are the kinds of bounds that we then use in the proof itself. So if you want to prove the sufficient condition itself, then there's another little lemma, which is basically kind of what bias. So if you have information, so we have two real analytic maps on some interval. If you have a bound of the function values, and you also know something, so between the difference you have a bound, but you also have a bound on the second derivatives of the functions themselves separately, then you can deduce a bound for the difference of the derivatives. And this sort of thing you can then, if you also have information about higher order derivatives, then you can improve this of going to even higher derivatives here by induction. Okay, and this is precisely the situation that we are in, because we know that our derivatives are bounded for all derivatives. So in particular, how the proof goes in a nutshell is that it's by contraposition. So we assume that the exponential separation fails, which is going to give us a sequence going off into infinity. Going to zero super exponentially fast, and a sequence of words of that particular length for which the functions are closer than this number. So this is the words that we are able to use. And we want to show that from these sequence of words, we can construct two words of the same length whose corresponding h functions are identical. Then that shows that we have a contradiction. Okay, so this is the main idea. And so from the sequence that we are given, there's a way of constructing the actual sequence that we want to see in the end. So maybe I don't want to say this precisely here and look at some other thing, but here is an important claim, is that given this sequence, we can still get super exponentially close bound on this kind of difference over here. And assuming this, there are basically two different cases that we have to handle. And in each of these cases, basically what happens is that we construct what should those two distinct I and j words be, for which we then show that the corresponding h functions are identical. In the two different cases, and precisely what we are using are these kinds of bounds, that is this bound and these bounds that we have on the derivatives. And this is also the point where we are using analyticity in a very strong way to be able to say that if you have the two functions agreeing on some sort of dense set like this, then you have equality everywhere. Okay? And there are two different cases that you need to consider, but the general gist is the same for the both. You construct your sequences and you show that the corresponding h functions are the same. And then the final step is to show that this claim is also true. This one here. And this is where we use explicitly that we have the super exponential, this guy here. So that's what you can use to show that you even have super exponential closeness in this sense over here. And also, I mean, it's not super difficult, to be honest. What you see is just writing out the definition. So if you want to determine the difference of this, you have a bound on this, and you can basically just bound this numerator up over here by something which looks like this. And this is exactly where we are able to use our assumption on the super exponential closeness, and the fact that if you have super exponentially closeness for the functions, for the difference of the functions, and you also know boundedness of the derivatives otherwise, then you can upgrade that to difference of the derivatives as well. And yeah, so from here, it's not too difficult to finish this up. So I think for now, I'll stop there.
Okay, you have more questions?
I have a question. You defined natural separations by the superroom for one x point for the interval, right? Yeah, actually, I wanted to know if you change the superroom to infinite, can you still give some nonlinear examples or something say we still have some enough examples? Since it's very useful study the algorithm if you have anything. But I just wanted to know. Even if some example is very nice.
I think there's a trick to supreme to. I think there's a trick to doing this. You have your points where you have the second derivative, sorry, the derivative expression is different. And then that means there's a neighborhood around that point for which they're different. And then you use the IFS to map an arbitrary point into this neighborhood. And then somehow there's actually an arbitrary word which maps both of them corresponds to, if it's prefixing or suffixing your words which have different derivatives by a single common word. Because somehow when you look at the second derivatives, I don't remember if it's, I think Gaetan probably knows that the prefix or suffix are the same way, then this doesn't influence what you see in the first derivative expressions. It's still strictly positive or strictly negative, maybe with a slightly smaller constant. So I think the answer is yes.
Really?
But if I change the words, I just not the same length, but make the derivative of the maps with the same length, I mean, it's not the same words IAG, but they just
I have zero idea, but I'm convinced by what I say.
Yeah, different. So your supremum is positive, your infimum is positive, but with different words, they different constant. So if you have a statement like for all n of infimum in the end, there is a significant such that two words that this second derivative divided by first derivative, with the second derivative by first derivative, at least delta apart, then you can find infinitely many words and delta by 10,000, such that you can find which the infimum, the second derivative divided by first derivative expression, or at least delta divided by 1,000. I think this is true. Yes.
All right.
So I want to know, so if you restrict to the case of polynomials, can you use transversality in a meaningful way here? That somehow, for our series, we can say that these can rule out double zeros, but I imagine the coefficients might go off, so you're not in kind of the standard transversality framework, but
I think the proposition, well, the sufficient condition, and which you can really use to check it, is somewhat, at least in a flavor of transversality, that you immediately say that I think the dilemma really says that you immediately very much separated away, even in the very first step. So it's not that using the transversality, because the transversality again relies on the geometric structure and don't care about higher derivatives, right? It's this is why the transversality also works for self-similar systems and non-conformal systems simultaneously. I care about your position and how much you contract, and that's it. And this is a little bit different, but in the flavor of look at the very first term and then ensure that the later terms, which are controlled by the first derivatives, are not too large, right? So it's a transversality for a different kind of way. So for if you wish transversality for the second derivatives, the second derivatives are immediately completed.
But you speaking in the general case of all IFSs, or just I was thinking particularly if you have IFSs which are defined by polynomials.
No, general IFSs. Again, I don't think that the transversality or any such kind of estimates, which only sees, our first few derivatives, but anyhow, you need all the higher iterates and so on, would make any difference between polynomials or whatsoever. Perhaps. This one is.
I agree. I think there's nothing special about polynomials with this condition. If you're talking about things like typicality or transversality argument. As far as this is already a strong condition on the first level iteration. But if you go to the actual transformation condition version there, that thing I would also strongly suspect holds generically for any way of parameterizing.
Yes. So what I would, suggest, this is what I would expect for polynomials that by some miraculous technical
easy way.
Easy way, brute forcing and killing several trees and writing things on paper. It might be that there is some very high iterate in your dual IFS where you can verify this tiny delta gap and have control for the higher iterates. Something very handy.
Yeah, in that sense, this is a sort of transversality, but we need to descend to the right enough level for a separation.
Okay.
Yes.
almost to the y and z, how are these chosen?
Oh, I do not recall at all. They come from some kind of some clever orbits, I think.
Yes, yes, some kind of you have to follow the orbit of some well-chosen points. I have no idea how these points needs to be chosen, and you follow the orbit of them, and exactly where you want to change things is the very last element of the orbit, and you want to keep all the other parts untouched. I don't remember. I remember that it was painful.
All right, then I'm going to give so much time to ask questions throughout the week, so let's thank István again.